It's a sad but inescapable fact some of the greatest advances in science have come from humanity's more destructive impulses. German chemist Fritz Haber, for example, figured out how to fix nitrogen from the atmosphere to create gigantic bombs used to kill people in World War I, but his technology was also used to make the world's first synthetic fertilizers, which revolutionized how the world feeds itself. Gunpowder, similarly, was discovered by ancient Chinese alchemists, but was developed by Europeans who used it to conquer half of the world. None of this is science's fault. When we discover powerful truths about the universe, it's up to us to decide how to use them, because they can either be boons to humanity or banes. And there's probably no better example of this than the work done by the Manhattan Project, the years-long multinational effort to develop an atomic bomb during World War II. It took $2 billion, roughly $25.8 billion of today's dollars, and 100% of the smartest chemists, physicists, and engineers in the US, UK, and Canada to develop and build 4 nuclear weapons. First, the Gadget, the test bomb that was detonated in the desert of New Mexico. Second, Little Boy, which was dropped on Hiroshima, Japan. Fat Man, dropped on Nagasaki, Japan. And a 4th bomb that was thankfully never used. It's because of those bombs that we now live in a world where humans have the wherewithal to destroy ourselves and every other living thing on the planet. And though they effectively ended World War II, atomic bombs started the Cold War, which was almost 50 years of everybody walking around worried that they were going to be incinerated at any moment. But the Manhattan Project is responsible for humanity gaining a lot of information about the atom, and really quickly. If it hadn't been for this top-secret bomb development program, all those physicists wouldn't have been able to collaborate to make this science happen. And it's science that we're still learning from today. Before we invented atomic bombs, humans destroyed each other and each other's stuff using conventional bombs, casings full of explosives like trinitrotoluene, that's TNT, or ammonium nitrate, or some cocktail of different explosive substances. When they're detonated, conventional bombs release most of their energy in the form of a blast, a wave of superpressurized air that moves out from around the bomb faster than the speed of sound, which is why they make that big booming sound. After the initial blast, which might be accompanied by a fireball, depending on what the bomb is made of, a vacuum is created around the site of the explosion and air rushes in to fill it, creating a blast wind that sucks everything into the detonation site. By comparison, an atomic bomb uses an unstable radioactive isotope of uranium or plutonium as the explosive. If you fire a single neutron at a single atom of one of those radioactive isotopes, it can split the atom and shoot out other neutrons, which in turn split neighboring atoms, creating a chain reaction of split atoms in a process called nuclear fission. All of this happens in about 1 picosecond, and then an unbelievable amount of energy and heat is released. The release is so powerful because it unleashes energy from the most powerful force known to physics, the rightly named strong force. Strong force is what holds an atom's nucleus together, pulling protons and neutrons close to one another, but also keeping them from getting too close. It's a very tense, dynamic kind of subatomic push and pull. To give you an idea of what it's like when energy from this force is released, 1 kilogram of nuclear fission fuel can release 20 million times more energy than a kilogram of TNT. About 50% of the energy released in a nuclear detonation is a blast, like a conventional bomb, 35% is released as heat, and about 15% is nuclear radiation in the form of gamma rays, neutrons, and alpha and beta particles. The radioactive pulse emitted when an atomic bomb is detonated continues to linger after a blast in the form of nuclear fallout, a kind of dust made up of unused and spent fuel that's begun the process of radioactive decay. Until 1932, nobody knew that any of this was even possible. That's when German-Jewish physicist Leo Szilard first theorized that nuclear materials could be used to create energy in a chain reaction, much like a chemical chain reaction. Mind you, this was 6 years before anyone even knew about fission, but Szilard thought that the key was the neutron, which had just been discovered. He figured that a neutron from one atom could be used to cause an energy-producing reaction in another atom, releasing more neutrons that could generate more reactions. And if the reaction was discovered that could free that first neutron, somebody could use it to create a pretty flippin' sweet bomb. So Szilard used the idea to patent the world's first atomic bomb, not because he planned on making one, but because if he held the patent for it, nobody else could make it. Smart guy. In 1936, Szilard turned his patent over to the British government so it could be classified under British secrecy laws to keep it out of the hands of the Nazis, who had come to power in Germany. And like many others who became involved in developing the atomic bomb, Szilard would later campaign feverishly against it ever being used. But from the perspective of many scientists, particularly those who knew what life was like under the Nazis and Italian fascists, not solving the scientific puzzle of nuclear fission was no longer an option. Because by the time World War II broke out in Europe, Szilard's hunch that fission was was possible had been proven by a team of physicists in Berlin. So in 1939, influential physicists including Szilard, Albert Einstein, who was Jewish and had escaped Nazi Germany, and Enrico Fermi, who had just escaped fascist Italy with his Jewish wife, started pressing President Franklin Roosevelt to start an atomic research program before the Nazis solved the puzzle first. Roosevelt responded by bringing together the brightest minds in physics, chemistry, and engineering to research how to make weapons out of uranium and plutonium, an element that doesn't occur in nature but can be made from uranium-238. It became known as the Uranium Committee. A lot of the most impressive and difficult science that we associate with what would later be known as the Manhattan Project was actually done by this committee, which included both military and civilian types, including Nobel laureates Ernest Lawrence, Harold Urey, and Arthur Compton. And at first nobody was even trying to make a bomb. They were just trying to figure out how to isolate enough of the right kind of uranium to create the chain reaction that Szilard had envisioned. Because the problem is that most of the world's uranium doesn't come out of the ground ready to be made into a nuclear weapon. Actually, that does not sound like a problem to me. That sounds like a good thing. Naturally occurring uranium is actually a mixture of two isotopes, or forms of uranium with different numbers of neutrons in their nuclei, uranium-235 and uranium-238. Because they have different numbers of nucleons in their nuclei, they respond differently to having a neutron shot at them. Uranium-235 will bump up to uranium-236, which is really unstable and will therefore undergo fission a lot more readily than uranium-238, which just absorbs that extra neutron and becomes uranium-239, which is super stable and not fissile at all. So most of the time and money involved in the committee's research was spent figuring out how to enrich uranium. That is, how to separate the uranium-235, which makes up less than 1% of the world's natural uranium, from the uranium-238. The committee eventually discovered that this could be done by combining uranium with fluorine to form a gas that could be filtered to extract the isotope that they wanted. But then they had to figure out how much uranium-235 was needed to achieve critical mass, the smallest amount of fissile material necessary to sustain a nuclear chain reaction. After that, they just had to figure out how fast a neutron had to be fired at the uranium atom to trigger a reaction. None of this research was easy, as you could imagine, but the physicists succeeded in answering all of those questions over the course of just a couple of years. By 1942, with these early puzzles solved, the project was turned over to the United States Army Corps of Engineers and moved to facilities given the code name Manhattan District. But the research actually continued at 3 labs in separate regions of the country, one in Oak Ridge, Tennessee, one in Los Alamos, New Mexico, and another near Richland, Washington. As the labs worked on enriching fuels and basically inventing whole new technologies to go inside the bombs, the project eventually came together at Los Alamos, where young American physicist Robert Oppenheimer, with the magnificent title Coordinator of Rapid Rupture, oversaw the bomb-making operation itself. And Los Alamos actually made 2 such devices, one fueled by uranium and the other by plutonium. The very first bomb, the Gadget, was a plutonium-fueled bomb that was detonated in the desert in southern New Mexico on July 16th of 1945 in an event codenamed Trinity. It was the very first atomic explosion ever to occur on Earth. When it went off in the early morning, observers 10 miles away immediately felt the heat of the blast and said that it was brighter than the sunrise. The test was a complete success, but afterward, Oppenheimer famously said it brought to mind a passage from Hindu scripture.
I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds."
And we all know what happened next. Within a month of that test, a plutonium bomb was dropped on Nagasaki and a uranium bomb on Hiroshima, killing at least 185,000 people. Soon, the war was over and the atomic age was beginning, a time when, if you wanted to, you could spend every second of your day worrying about whether the world was going to get blown up by people who happened to have gotten their hands on a whole bunch of enriched uranium. It also heralded the beginning of the Cold War, a period of about 50 years in which the United States and the USSR had nuclear warheads pointed at each other all the time, every day. It was terrifying and very tense. But the research done during the Manhattan Project was huge in helping develop nuclear energy, which has had its ups and downs, but it's incredible technology nevertheless. We also have the Manhattan Project to thank for the entire field of nuclear medicine, where radioactive materials are used in medical imaging, diagnosis, and treatments, like for some kinds of cancer. Even modern stem cell research has its roots in the Manhattan Project. And of course, course, the new understandings of the atom that we obtained in just a few short years brought about enormous advances in nuclear chemistry and nuclear physics that might otherwise have taken generations. Basically, in the 1930s and 40s, we did the impossible. We took the smallest, most seemingly indivisible particle in the universe and we found a way to split it, all so we could make the worst weapon we ever imagined. But we've used that knowledge for a lot of good since then, so I think the take-home here is science can be complicated, but so can history. Thank you for watching this possibly frightening, hopefully enlightening episode of SciShow. If you have any questions or comments or ideas, you can find us on Facebook and Twitter, and of course down in the comments below. And if you'd like to continue getting smarter with us, you can go to youtube.com/SciShow and subscribe.